log base 10 of I divided by I sub naught. And now, in order to get rid of the logarithm on the right-hand side, what do we have to do? We're trying to get I out of the argument of the logarithm, so what do we have to do?
Someone. I think Tuesday.
Well, we have to take 10 to the power of both sides. So let me just write that down to explain what I'm doing. So this, the left-hand side becomes 10 to the beta divided by 10 decibels, and the right-hand side simply becomes I divided by I sub naught. So finally, I is just equal to 10 to the beta over 10 decibels times I sub naught. What is beta? Like, what's the value of beta? In part A. You know what beta represents?
110?
Yeah, it's the sound intensity level. It's 110 decibels. So this is 110 decibels divided by 10 decibels times I sub naught, which is always 1 times 10 to the minus 12 watts per meter squared. I sub naught is a constant. It's not different for different problems. It's always the same. Okay, and 110 divided by 10 is just 11. So this is 10 to the 11th times 10 to the minus 12 watts per meter squared. And just out of curiosity, do you know what that is, 10 to the 11th times 10 to the minus 12?
Shouldn't it? Yeah. Shouldn't it just be a number with no...
Huh? You really don't know, or it's just like really late and you're kind of tired? Okay, well, you know, when you're multiplying two things that are to different powers, basically what you're doing is you're adding the powers, all right? So 11 minus 12 is just negative 1, right? So it's 10 to the minus 1, or 10 to the minus 1 watts per meter squared, which is 0.1 watts per meter squared. Okay, so let me put a box around that and go on to part B. In this question, we want to know what the intensity will be, or what the new sound intensity level will be at a shorter distance. Okay, so the first thing that we have to do is find the new intensity. And there's a simple relationship. We know that I is equal to P source divided by 4 pi r squared. And So I varies with the inverse square of R, and what that means is that I2, or let's go ahead and use more meaningful subscripts. We can say that I far divided by I near. Oh, wait a minute, we're trying to find is I near. Okay, so let's put I near on top. I near divided by I far is equal to R far squared divided by R near squared. So if we solve that for I near, since we're trying to find it at the closer distance, this becomes R far squared divided by R near squared multiplied by I far. I have to scroll back up here. Okay, our R far is 25 meters, our R near is 7.9 meters. So we have 25 meters squared divided by 7.9 meters squared multiplied by the intensity at the greater distance, which is 0.1 meters, or watts per meter squared. So this is, let's see, 25 squared divided by 7.9 squared times 0.1 is 1.00 watts per meter squared. But obviously that's not the answer. Okay, that's the intensity at the new distance. What we need is the sound intensity level, which is different. Okay. So in order to get the sound intensity level, the new sound intensity level, now that we have the new intensity, we're going to say that beta near is equal to 10 decibels times the log base 10 of I near divided by I sub naught. And that is 10 decibels times the log base 10 of our I near is 1.0 watts per meter squared divided by 10 to the minus 12 watts per meter squared. So what's the inverse of 10 to the minus 12? Anyone? Anyone?
10 to the 12?
Yeah, 10 to the plus 12, right? When you take the inverse, all you do is change the sign of the power. So this is 10 decibels times the log base 10 of 10 to the 12. And what is the log base 10 of 10 to the 12? Well, the log base 10 of 10 to the 12 is the power to which you have to raise 10 in order to get 10 to the 12. So what power is that? 12, right? Okay. And so that's where we got our 120 decibels. But there's still one more part of the problem to go.
How did you know you were supposed to be looking for I
How did I know? Oh, well, we already calculated IFAR. See, that's what this is. In part A, we calculated the original intensity. That was at the further distance, okay? So I didn't actually write this as IFAR, maybe I should have, but that's what we calculated in part A. And what we're asked for in part B is the intensity or sound intensity level at the nearer distance. So part C is just a matter of finding the right equation and plugging in numbers. I've already given you the equation relating intensity and power output. I is equal to P source divided by 4 pi r squared. Now, we're solving for P source, and so that is just 4 pi r squared times I. Now, we can use, the power of the source is a constant. It doesn't depend what distance. So we could use either R far and I far or R near and I near, as long as we're consistent. We don't mix them up and say R far and I near or R near and I far. So let's go ahead and use R near and I near. R near was 7.9 meters. I near was 1.0 watts per meter squared. And that should give us our 785 watts. Well, let me check to make sure. Yeah, it comes out. Well, close enough. Probably some rounding error in there. But anyway, does anybody else have any questions about this problem? Or any problems with this question? Okay. Pretty sure we didn't do this one. Nope, we didn't do this one. Okay, so on problem 7.
I kind of like hacked it once.
All right, so this is a pair of narrow slits. So we're dealing with the formula for two-slit diffraction, or two-slit interference, rather. And that is simply, whoops,
Could you just get a hit, like
Ym bright
a case or something?
is equal to M lambda L over D, where M is equal to one of the, it starts with 0 actually, one of the non-negative integers. And so we're told the wavelength, the slit separation, and we want to know the spacing of the bright fringes. So first of all, if we look at the interference pattern, it's something like this. This is the center of the pattern.